Hi, I'm John Ackermann, N8UR, and thanks for stopping by today while we consider the history of timekeeping from sundials to atomic clocks. Before we begin, just a word. If you make it to the end of this presentation, you'll realize that I could talk about this stuff for a long, long time. And to fit with today's schedule, I had to remove quite a bit of material from the presentation. I'll be uploading a set of slides that includes all that material. So if you find this interesting, I suggest that you come back and download the full slide deck because it's going to cover some things that we don't have time to talk about today. I suppose it's useful first to try to define time. On the left is one attempt. Einstein discovers that time is actually money. And immediately after that discovery, lawyers started to bill by the hour. Another definition comes from a 1921 science fiction story, The Time Professor. It's time is what keeps everything from happening at once. Now that's a clever line and pretty funny, but it's actually got a lot of truth to it because another thing that Einstein discovered is that time is a dimension. It's one of the four known dimensions of our universe. We live in space-time. And without time, we wouldn't have a past, a present, or a future. We wouldn't have what physicists call the arrow of time. And that concept is critical to the way we think the universe works. We wouldn't have entropy or the laws of thermodynamics or chemical reactions that take time to progress if we didn't have time as a dimension. So this is a funny line, but it's also not a bad way to think about it. In the real world, when we talk about time, we can mean a number of different things. First, of course, is the time. It's now 11:59:59. When we say that an event happened at a specific time, what we're really doing is placing that event on a time scale. A time scale starts from a known starting point, like midnight, and it progresses or increments at a fixed rate, like once every second. Now, this sounds a little bit like angels dancing on the head of a pin, but there are actually a number of different time scales out there. And it's important to know which one we're using. And we'll talk about that a little bit more later on. Time interval is another way to look at time. It's a time between two events that occur on a time scale. Think of a stopwatch. Click the button again, and the display will tell you how much time has elapsed. That's time interval. And it's extremely useful. It lets us know how long something takes. It lets us compare the length of different events. And in timekeeping, we also use it to compare when my clock ticks compared to yours. Period is the time interval between the repetitions of a single clock. So if I have an oscillator that's running at 100 hertz or 100 cycles per second, its period is 1/100th of a second. As hams, we love frequency. And frequency is just the reciprocal of period. So if my oscillator has a period of 1 millisecond or 1/1000th of a second, that means its frequency is 1 kilohertz or 1000 cycles per second. And that relationship holds no matter what numbers we use. We should also understand just what a clock is. There are three components in any clock. The first is an oscillator, something that repeats at a constant rate. The next is a counter that tracks the number of oscillations that have occurred. And the third is an indicator that shows the counter value at any given moment. When I talk about clocks today, I'm almost always talking about the oscillator. It's the interesting part. It's what establishes the quality of the clock. It's what technology has affected the most. The counter and the indicator are interesting in their own way, but the oscillator is what's really cool. So today in this presentation, when I say clock, you can think oscillator. And as hams, you're also allowed to think frequency standard because a lot of clocks that have oscillators also can use them as frequency standards because they're running at an RF frequency. Well, what would we like to know about a clock? Well, first, how accurate is it? How does it compare to WWV? We'd also like to know its rate, which is how fast or slow it runs. Does it gain a minute per day or lose a second per hour? If we know that, if we know its rate, we can calculate how much error has accumulated since the clock was synchronized against something like WWV. So the rate is a very useful piece of information. We'd also like to know how stable a clock is. It's going to change in frequency over short and long time periods, and we'd like to know how much. We'd also like to know how sensitive the clock is to environmental variables. Does temperature cause it to speed up or slow down? It does, by the way. But understanding the magnitude of those changes is very important to understand how an oscillator works. This is not exactly a high-tech graphic, but I like it because it shows the relationship between accuracy and stability. On the left, we have a signal that's stable. It's a horizontal line and it doesn't have a whole lot of wiggles on it, but it's not accurate. It's above where the frequency should be, where the dashed lines are. The second panel shows us a signal that's neither stable nor accurate. It's not where it should be. In fact, it's changing frequency continuously. And while it's doing that, it's bouncing around. That's the worst of all possible worlds. The third panel is a really interesting case because it's very common and something we have to deal with. In this example, if we looked at the average frequency over the time that's shown, we'd find that on average, the frequency is the same as the dashed line. It's accurate. But at any given moment, a measurement that we take might show a very different number, and that's because the oscillator is not stable. And this is a real important factor because when we're trying to look at oscillators in the real world, sometimes their stability masks, or their instability masks the ability to determine how accurate they even are. The fourth panel is what we would like, of course, a signal that's both stable and accurate. It's important to keep time in perspective because we can be talking about trillionths of a second or billions of years, and that's a lot of zeros either to the right or to the left of the decimal point. It can become hard to see the forest for the trees. Often what's important is the difference of the actual frequency from the nominal frequency. In other words, how far off is it from where it should be? And we can express that as a ratio. Take that 100 hertz oscillator. If it's stamped on the can that it's 100 hertz, but I measure it and it's actually running at 99 hertz, well, that's an error of 1 hertz out of 100, or 1%. And that's a really useful way to characterize the performance of an oscillator. It's also very useful to use scientific notation because, yeah, we have this huge range. So for example, a 2.3 hertz error at 1 megahertz is 2.3 times 10 to the minus 6th, or 2.3 parts in 10 to the 6th, or 2.3 parts per million. They all mean the same. And by the way, I'm going to make a mistake today, I know, and say parts in the 10 to the minus something when it should be positive something. It's an awfully easy slip to make, and I beg your indulgence because I'm certainly going to do it. Well, now we can finally talk about some history. The first clock that humans had was the sun. And to start with, we really only knew about day and night. But it wasn't long before sundials were invented, and they allowed us to divide the day into shorter periods like hours. Of course, they didn't divide the night, and they didn't work so well on a cloudy day either. Sundials had a problem, though. The length of the day varies over the year, so the divisions that we make change over the year as well. If we divide the daytime into 12 hours, each hour is going to be longer in the summer than it is in the winter. And we call that apparent solar time. It's a time that's based on the actual apparent position of the sun. That's not very useful because it's hard to compare times when the lengths can be different. A way around that is to use mean solar time. And mean solar time is simply time that's based on the average length of a day throughout the year. The apparent and the mean solar time can differ by as much as 16 minutes, so it's not a trivial thing. If you know where you are on the Earth and what day of the year it is, something called the equation of time will let you convert apparent solar time from a sundial into mean solar time. But that's complicated, and we really don't want to have to do all that work. So our goal has been to find clocks that don't rely on the sun. The very first non-solar clocks were actually more time interval measurement devices or timers than actual clocks. We discovered that we could divide time with hourglasses. The sand runs out in a certain amount of time. A water clock, the bucket fills at a certain rate. And by the way, on the right-hand side, here is a picture of a clepsydra, which is a form of water clock. But we might even have a candle that burns 1 inch per hour. Now, these all have reasonably uniform time periods compared to a sundial, but they all will only run for a limited time before they need to be recharged. You have to flip the hourglass over, et cetera. And that means that there's a time when that's happening when you're not able to actually measure. You lose time while you're making the changeover. So these devices were more practical for measuring time interval than actually keeping time. And of course, we ultimately would like to keep time, so we kept advancing. Mechanical clocks appeared at about 1400, and the first ones were steeple clocks driven by weights falling due to gravity. And these clocks were able to show half and quarter hours. Then in about 1450, we saw the first spring clocks that had minute hands, and a second hand appeared on the clock in about 1560. Around 1650, there was a huge advance when Galileo did his experiments with pendulums and discovered that a pendulum of a given length has a remarkably constant speed of its swing. And that was very quickly turned into the basis of a clock. And pendulum clocks were quite good. They were much better than anything else. They did have one disadvantage. They want to be anchored to solid earth. They don't work very well when they move around. And unfortunately, one of the places where accurate time is the most important is on a ship at sea that's trying to navigate. To know what your longitude is, how far east or west you are, you need to know the time. And a pendulum clock does not work on a ship. This was such a big deal that the English government in the 18th century instituted an award for the first person who could come up with a way to navigate from the Atlantic to from the eastern side of the Atlantic to the Caribbean within a certain amount of accuracy. A fellow named Harrison took up that challenge, and he built a few big clocks first that weren't quite good enough. And then he changed gears, and he built a very small clock. It actually looks more like a very large overgrown pocket watch, but it was very, very precise. And in 1761, that watch, the Harrison chronometer, took a trip from England to the Caribbean. And when they got there, they were within where they should have been based on the accuracy of the chronometer. So Harrison qualified for the prize. Unfortunately, he didn't live happily ever after. There was a lot of politics and backbiting and frankly, a lot of whining going on. And in the end, he got some money, but it was an awful experience. There's a great book called Longitude by Dana Savell that tells this story, and it's really a great read. I recommend it. Pendulum clocks kept getting better during all this time. And by the end of the 19th century, there were what we call free pendulums that swung in a vacuum, so there was no air resistance, and had electromagnets to give them a kick rather than a mechanical gear. And they had an electric sensor to detect the motion rather than a mechanical connection. And all these things reduced the drag and allowed the pendulum to be more accurate. The best of these clocks were accurate to less than 1 second per year. That's about 3.18 times 10 to the minus 8 if we're using the terminology we talked about. And a recent evaluation indicates that the accuracy may actually have been more like a second in 12 years. It's pretty remarkable. Now, if you step back for a minute and look at this chronology, to me, it's apparent that our perceived need for accurate timekeeping increased along with our ability to provide that accurate time. When we were an agrarian society, we really only needed to know what time it was to come in for lunch. But as we moved into town and we had shops and other businesses, we wanted people to know when they were open and to show up on time. So half and quarter hours were helpful. And minutes were even better because now we could show how long we had worked in the factory more accurately and get paid for all of our time. Seconds were useful for scientific purposes, but also for sports, to time the speed of a horse on a race. And we see this, we need better accuracy, and the accuracy becomes available. And I just wonder, what was the driving factor? Did technology drive the need, or did the need drive technology? I just think that's something interesting to ponder in a spare moment. The 20th century ushered in the electronics age. And in about 1920, quartz crystal oscillators were developed. And it wasn't long before it became apparent that they might serve as very good clocks. By 1930, quartz oscillators were stable to about 1 times 10 to the minus 7th, or 1 hertz at 10 megahertz. By 1938, that had doubled to 5 and 10 to the minus 8th. And that was approaching the best pendulum available at a much lower cost in bulk. And by the early 1950s, The best oscillators were stable to a part in 10 to the 10th. And that just leaves mechanical clocks in the dust. So quartz oscillators were really important and a giant advance. However, they did have some problems. First, a quartz oscillator doesn't automatically run at the right frequency. The frequency is affected by the way the quartz slab is cut apart, by the thickness and other dimensions of the piece of quartz, the way it's mounted between electrodes, the circuit it's operating in, the temperature, et cetera, et cetera. So when you first turn a quartz oscillator on for the first time, you don't actually know what frequency it's going to have. You might have a guess, but you need to calibrate it against another known source to know what frequency it's really running at or to adjust it to the frequency you want. To make things worse, quartz oscillators also suffer from an effect called drift or aging. If I set the oscillator to exactly the right frequency today, and I come back a week from now, I might find that the frequency is now 1 part in 10 to the 8th low. I might come back a week later and find it's now 2 parts in 10 to the 8th low. And that increasing error causes a time error to accrue very rapidly. As the clock becomes more and more off frequency, it falls further and further ahead or behind. And to make things even worse than that, I might come back the 3rd week and find that the clock is now running 1 part in 10 to the 8th fast. So we can't predict what it's going to do. And so as a result, crystal oscillators need a recalibration to take the aging effects into account. Crystal oscillators also are very temperature sensitive. We joke that every oscillator is a thermometer, and that's really true. And the best of those 1950s clocks that were parts in 10 to the 10th kept the crystal and the critical oscillator parts in an oven within about 1,000th of a degree centigrade. That's what it took to maintain that kind of stability. But these types of oven-controlled oscillators were really the state of the art through the 1950s. Well, now with the quartz oscillator, we had a clock that had a tick that was very regular, much more regular and precise than ever before. And that made scientists and astronomers realize that they needed to agree on just how long the second was. And particularly for astronomers who are timing the transit of celestial objects, and they want to compare notes with someone somewhere else. If you don't agree on how long a second is, you'll never agree on the time. Until 1956, the definition was simply 1/86,400th of a mean solar day. 86,400 is 60 seconds times 60 minutes times 24 hours. That just wasn't good enough. So the astronomers and scientists got together and developed a new definition that came into effect in 1956. This new definition, instead of being based on the rotation of the Earth around its axis, is based on the revolution of the Earth around the sun. In other words, it's based on the year rather than the day. And it's now a fraction, there's a 31 billionth or something of a year, but not just any year, the year 1900 measured in a specific way. And this was a really big improvement, and it was known as the ephemeris second. And the folks were pretty pleased with themselves for coming up with this, but then everything changed. In the 1920s, as well as developing oscillators, scientists started to discover quantum physics and to understand that subatomic particles like electrons were governed by their own rules. And these were rules that Isaac Newton could never have contemplated. One of those rules is that the electrons surrounding a nucleus in an atom can only exist at certain energy levels. And they jump from one level to another with no in-between state. They are literally either here or there, and you can never catch them in the middle. For that to happen, they absorb a photon, and a photon is a packet of electromagnetic radiation. It could be RF or it could be light. They absorb a photon, and that makes them jump up into a higher level or an excited state. And then later, they may release a photon to move back down to the original or the ground state. That's the conservation of energy, a photon in and a photon out. Now, this absorption and emission is what causes the black lines in an optical spectrum. If we put a prism in front of a light source, we'll see the rainbow. If we look very carefully, we'll see black lines at various places. Those black lines are places where the atoms in the light source are absorbing the photons of light to move into a higher state. They provide us with knowledge about what elements and chemicals are part of that spectrum. This is really important for astronomers because it lets them tell what stars are made of. We learned about absorption lines and also emission first with astronomy, but that stuck in the back of people's mind, what does it have to do with clocks? Well, in World War II, we had huge advances in nuclear physics because of the atomic bomb project. And we also had huge advances in microwave radio because of radar and other radio developments. There were some physicists who worked in both of those projects, and they came up with the idea of an atomic clock. Could we lock a clock to one of these atomic lines or resonances rather than to a pendulum or a crystal? The idea would be to hit a specific atom with energy at precisely the right frequency to make it absorb photons, and then measure that absorption and steer the energy source to be exactly on the right frequency to maximize that. If we do that, then our oscillator will track the atomic resonance and have its stability and accuracy, and that would be a pretty cool thing. Here's how atomic clocks work. There are many different types and they have slightly different mechanisms, but here's a rubidium standard, which you might have heard of. You can buy them on eBay pretty cheaply. And it's based on rubidium light, a lamp that's full of rubidium gas shining with its own spectrum through a glass cell that's also full of rubidium gas. And there's a photodetector that senses how much light is going through the cell. We pump in RF at about 6.8 gigahertz. And when we're right on frequency, some of the atoms in the rubidium cell will absorb some of the light coming from the lamp. And the detector will see that. Its output will go down. We can use a servo to adjust the frequency of the crystal oscillator that's generating the signal to keep it right where the maximum dip in brightness occurs. And then we tap that 10 megahertz out, and we have a signal that's locked to the atomic resonance and is much, much more stable than the crystal oscillator would be by itself. Other types of atomic clocks, again, use different atoms and they work a bit differently, but the same basic concept of looking for absorption and tracking a signal to maximize the absorption is the way that almost all atomic clocks work. The very first atomic clock was built by the US National Bureau of Standards in 1947. And the guys who built it really were thinking about PR, because that's a really cool looking box. It's big and it's got knobs and dials and it's got a big clock on the top. And the thing that winds around the clock is actually a piece of waveguide that's full of ammonia gas, because the clock worked on the absorption of ammonia gas at about 24 gigahertz. Now, unfortunately, as cool as it looked, it didn't work all that well. Its stability was about 1 in 10 to the minus 7th, which is worse than most crystal oscillators. And it could only run for a few hours at a time. So it really couldn't be a clock. But it proved the concept, and it showed that perhaps with other substances, we might do better. It turns out that the element cesium is an ideal element to use for this. Cesium is a soft alkali metal, has a very low melting point, not much above room temperature. And its atomic structure is ideal for clocks because it's got a whole bunch of electrons in the outer shell just waiting to be hit with some RF and jump up. So what we do is we send a beam of cesium atoms through a cavity that's full of RF at about 9.192 gigahertz. And when that frequency is just right, the electrons will jump up, and that change of state impacts the way the atoms go through a set of magnets at the far end. The atoms that have had their state changed will react differently than the ones that haven't. So the magnet steers the changed atoms to a detector, and a servo loop adjusts the frequency to get the maximum response. And that's how a cesium clock works. It's very similar to the rubidium, just using a different mechanism. Cesium turns out to be a great choice because it has only a limited impact from the external factors like magnetism and gravity and things like that. And you can compensate for a lot of those with shielding, or you can at least calculate how much effect they have. And in particular, a cesium clock has virtually no drift. If I measure a clock today and I come back a year later, that cesium clock will be at still the same frequency. It won't drift at all. And that makes it a very, very good clock indeed. Really, the only downside of a cesium clock, other than its expense, is that it burns up all of its cesium after maybe 3 to 10 years, so it has to be rebuilt or replaced. Here are pictures of some historic cesium clocks. On the left is a clock being built at the NBS starting in about 1950. But unfortunately, after taking a lead with the ammonia clock, NBS was hit with political issues and budget cuts and all sorts of horrible things. And attention turned away from the atomic clock, and it was never completed. That left an opening for the National Physical Laboratory in the UK, and Dr. Essen, who's shown on the right in the right-hand picture, to build the first working atomic clock, which started operating in 1955. So the UK took the lead from the National Bureau of Standards, but very interestingly, well, NBS fell back. A commercial company in the US, a national radio, which some of you might have heard of if you are interested in old-time radio gear, decided that they could create a commercial atomic clock. And they worked with some of these same physicists and developed the Atomicron, which they started selling in 1956. So that was only about a year after the NPL clock started working. And National sold about 50 of these, most of them to the US government. In the lower right of the picture is a current cesium standard. This is a model 5071A that was originally introduced by Hewlett-Packard in about 1990. The line has since been sold and it's had a number of different names, but the same unit is still in production today, and it still is the atomic clock of reference in many, many laboratories. So even though it's a 30-year-old technology, it's still finding very wide use today. Now, a beam clock, like we've been discussing, that shoots a beam of cesium atoms through some magnets and RF, has some inherent limitations. And the smart guys figured out another approach that might get better performance out of a cesium clock, and it's called a fountain. And I think this is just absolutely magic. The idea is that you take a ball of cesium atoms, a little cloud, and you get it in between a bunch of lasers. And in my little brain, if you put something between a bunch of lasers, it's going to get hot. But the way this actually works is that the lasers cool the cloud of atoms down to almost millionths of a degree within absolute zero. And at that low temperature, the atoms move very, very slowly. And then a laser gives a little push, and the cloud of atoms floats upward, and it goes through the probe laser and the detector, and then it travels up through the microwave cavity and travels back down and hangs around to be probed again. And this whole process might take 100 seconds. So it's moving very slowly, which means you can measure the signal for a long time and get a better signal to noise ratio. Also, because the atoms are moving so slow, the Doppler effect, which is an issue with beam clocks, is almost non-existent. So a fountain clock can give us better performance than the beam clock. And the National Institutes of Standard and Technology, NIST, which is the follow-on to NBS, fountain clock F2, has an uncertainty of about 1 part in 10 to the 16th. That's about an order of magnitude better than the best beam clock. And it's believed that this is about as good as cesium is going to get. There are some inherent limitations that are going to stop us from having any more huge improvements. Well, now we have an even better, more regular clock that ticks even more regularly. And remember, in '56, which is just about when the Atomicron started selling, the second was defined in terms of the tropical year. Well, just as that was going on, NPL and the US Naval Observatory, which kept a very accurate astronomical time scale, and NBS, which ran WWV, worked together to compare the frequency of the NPL clock against the US Naval Observatory timescale. And they did this for 3 years to measure the cesium frequency. And they came up with 9,192,631,770 plus or minus 20 cycles per second. Now, later lab measurements showed that this was really remarkably accurate, and it was better than the technology available to them should have allowed. So these guys were not only great experimentalists, but they also had some luck on their side. And given that we have this incredibly accurate measurement of a second in terms of billions of cycles, it's sort of inevitable that we'd be looking at a new definition for the second. And in 1967, that happened. The second was defined as the duration of those 9 billion something periods of the cesium transition. What's really interesting is that the tables have turned. First, we measured the cesium frequency against the second, and now we measure the second against the cesium frequency. I think that's just really cool. And I'll also note that there was a minor change in the definition in 2019 that further specified the test conditions, but it didn't really impact the basic definition at all. Well, now we have a clock that ticks with an extremely regular rate, and we've defined the second very precisely in terms of that rate, but we still don't know what time it is. In most countries, the legal time is based on UTC. UTC is the acronym of the French words for Coordinated Universal Time. And it's a time scale, remember that word, that's maintained by an international agency based in France. It's based on something called TAI. Well, TAI is another time scale. It's the French acronym for International Atomic Time, and it is the time scale of the very regular ticks of atom clocks running in laboratories around the world. So UTC is based on TAI, but it adds leap seconds. Leap seconds? Well, it turns out that the Earth's rotation is slightly irregular, and it's generally slowing down over time. And if we kept our clocks just to atomic time that's incredibly regular, over a long time, we might find that noon happened at night because the atomic and the solar time had diverged so much. And people generally thought that wasn't a good idea. And they thought of a number of different ways to address it. And the best idea they could come up with was a leap second. So what happens is when the rotation of the Earth causes a solar time to vary so that UTC is about 9/10 of a second different than the atomic time, we insert an extra second or potentially remove one, although that's never happened, at midnight on either June 30 or December 31st. So the clock goes 23:59:59, 23:59:60, 00:00:00. And that keeps solar time, human being time, in sync with atomic time. The problem is that things like computers don't deal with leap seconds very well at all. And there are ongoing religious wars. There's a mailing list devoted to nothing but discussion of leap seconds, and people want to get rid of them. The problem is no one has come up with an alternative that makes everybody happy. So although nobody really likes the leap seconds, there's not been a better idea that could have a consensus developed. So we're still stuck with them. And the chances are we'll be stuck with leap seconds for quite a while. And I'll just mention before we leave the topic of timescales that as hams, we might use GMT in our logbooks, and we think that GMT is the same as UTC. It's really not. GMT is based on adjusted solar time at the Greenwich Meridian in England, and it can be up to about a second different than UTC, depending on the amount of Earth rotation change. So for practical purposes, they're the same, but if you want to be accurate, you should use UTC in your log rather than GMT. I mentioned that cesium clocks have gone about as far as they're going to. So what's in the future? Well, the next step appears to be optical clocks. And the idea is that these absorption lines that we see don't change a whole lot in their width, depending on the frequency of the radiation. So at a higher frequency, you can get a line width that's not all that much greater. And that's the same thing as having a tighter filter or higher Q. It gives you better signal to noise and you can get a more accurate measurement. The problem was that in the past, it was extremely hard to lock a beam of light to a single frequency accurately enough to be able to use it for an optical transition. That problem was solved by the optical comb that was invented over the last couple of decades. And the optical comb generates multiple different frequencies of light that are spaced by the amount of an RF frequency that's injected. And by using that, they're able to lock the RF frequency to the optical absorption line and create a clock that works that way. A lot of different elements have been tried. One of the most promising seems to be strontium, and a number of laboratories, including NIST, have developed strontium optical clocks. The NIST clock is estimated to have an accuracy of about 2.5 times 10 to the minus 19. That's 1 second in 200 million years. It's about 3 orders of magnitude better than the cesium fountain. And given that kind of accuracy, it's, I think, inevitable that the second is going to be redefined in terms of one of these optical resonances somewhere in the next 10 to 20 years. The optical clocks will have to become better proven. They'll have to decide which element is the best. The reliability will have to increase. But all those things will happen. And at some point, the second is going to be redefined in terms of the optical transition of some element. I've talked today mainly about the cesium clock because it's the most widely known and it's the one that ties directly into our timekeeping. But there are a number of different types of atomic clocks that are available and are widely used, more often as frequency standards than actually as clocks. They use different atoms, different architectures, because they meet different requirements. Because you can have optimization for size, power consumption, lifetime, cost, performance, but not all of those at once. There are always trade-offs. So different clocks are intended for different purposes. Well, first is the rubidium. We've already mentioned it. And a rubidium frequency standard can have very, very good short and medium term stability. And there have been laboratory versions like the HP 5065 shown in the upper right that are highly valued, even though they've been out of production for more than 30 years, because for time interval measurements from seconds to hours, they're very, very stable. But there's also another type of rubidium standard that's very small and inexpensive. Cellular base stations require very accurate time and frequency, and quite a number of the base station manufacturers use a rubidium standard to accomplish that. Now, these are much smaller, and they are much less expensive, and they have much less performance than that HP 5065. But they've been manufactured in very large numbers, and they show up surplus on eBay, sometimes for less than $200. Now, a rubidium standard, and particularly the telecom types, do drift over time, and the telecom versions are not as quiet in the short and medium term as the laboratory versions, but their drift is much, much less than a crystal. And that makes them attractive for, say, microwave ham operators who want to take their station out in the field and have a frequency reference that will work when they're away from home and perhaps their other frequency standards. At the opposite extreme of those little telecom rubidiums is the hydrogen maser. The maser locks to the 1420 megahertz hydrogen emission line rather than absorption. And if you are interested in radio astronomy, you've almost certainly heard about the 1420 megahertz hydrogen line, because there are huge clouds of hydrogen gas out in the galaxy that are amazing in generating RF at that frequency. And the hydrogen maser works the same way. Its advantage is that it has unsurpassed stability. It's parts in 10 to the 16th per day. And for any kind of measurement from seconds to months, it's the best you can get. These are very widely used in radio telescopes because it's important for things like very long baseline interferometry, where two telescopes far from each other combine their data, that the timing be very precise at both ends. And the hydrogen maser is stable enough so that if the clocks are initially synchronized, they stay put with respect to each other. So probably the majority of hydrogen masers are located in labs. They're not perfect. For one thing, they're not intrinsically accurate. There is ways that you can move the frequency around, so they do need some initial calibration. They do drift just a tiny bit. Perhaps the biggest thing is that they're large and expensive. The picture on the right shows a very early, almost an experimental version, but you can see the size, and the modern ones are not all that much smaller. On the left is the complete unit. On the right, the physics package, as it's called, has been cut away to show all the different layers of mechanical and thermal shielding, and the magnets and the vacuum pumps and things like that. And all of those go together to make these very expensive. the last time I checked, you could buy a new one for about $250,000. So you might want to get a spare as long as you're at it. They also need replenishment every 10 or 20 years, and that's not trivial, but after you spent that much money, I suppose you don't mind paying that. Finally, another type of atomic clock is very new indeed. It's the chip scale atomic clock, or the CSAC. This is an atomic clock that's reduced to the size of a large integrated circuit. They use a laser that shines through a tiny blob of vaporized cesium or sometimes rubidium. They're very, very small. They're very low power, and they're relatively low price. I think you can buy a new one for about $2,000. But they're much less stable than a real cesium clock, or for that matter, any other kind of atomic clock. And they drift quite a bit. However, their drift is less than a crystal oscillator of the same size and power consumption. These things are intended mainly for military applications, where you can picture the need for a portable and low power frequency source for crypto or communications gear or for navigation or whatever. And I think that's the primary market where these are used. Well, we have talked about sundials and chip scale atomic clocks and a lot of things in between. I'm very happy to take any questions that we have in the time remaining. And again, there is an updated, fuller version of the slide deck available for you to download that covers some things that we weren't able to talk about today. Thank you very much.